Welcome back. In this lecture in power electronics, we will continue our discussion on control rectifiers. We will focus on half control bridge rectifier. Let us see the outline. So in half control bridge rectifier, we will be discussing on three important loads, that is the resistive load, the combination of resistance and inductance, and the presence of the induced EMF, which is for the motoring action, that is the RLE load. We will do the performance analysis with high inductive load as well as the center tap transformer with the leakage inductance. What is the role of bridge rectifier when there is a source inductance, and performance parameters of these controlled rectifiers. The circuit configuration of half controlled bridge rectifier. The key features are it formed by replacing the two thyristors of a full converter with the diodes. We have seen the full converter, and in the full converter the thyristors will be replaced by the diode for only the two thyristors. What is the advantage? It produces the cost-effective solution with reduced control complexity. When we talk about the configuration, there is symmetrical configuration in the common cathode mode and the common anode mode. And there is asymmetrical configuration. So we will see the symmetrical as well as asymmetrical configuration. The advantage what we have is that the common cathode type is mostly common used, and it is simple in terms of triggering for both the thyristors, and it is a simplified control scheme. So we have the symmetrical configuration in the common cathode mode, which is the most common and having advantage as single triggering and simplified control scheme. So these are the circuits for the half wave single phase control rectifier. So here you can see the common cathode mode, the common anode mode, and the asymmetrical mode. So A, you can see there are two thyristors T1 and T3, and there are two diodes D4 and T2. Similarly, here in the common anode mode, the thyristors are below and the diodes are above. And here what we have in the asymmetrical mode, this is not in the symmetrical fashion. So we have the thyristors on the left and the diode on the right. So we will see this operation of half wave control bridge rectifiers. The operation principle: in the positive half cycle, the thyristor T1 is forward biased, and we have seen that omega t equal to alpha, always the triggering will be done when we apply the pulse. The thyristor T1 will turn on and the current will start flowing from thyristor T1 through the diode D2. At omega t equal to pi, the thyristor T1 is reverse bias and it will turn off. What happened in the negative half cycle? The thyristor T3 is now forward biased, and at omega t, which is pi plus alpha, the triggering pulse will be applied. So T3 will turn on and current will start flowing through T3 and D4. Omega t 2 pi, the T3 will reverse bias and turn off. So one complete cycle is done where both the thyristors T1, which is in the forward biased conduction, takes place, and the thyristor T2, T3 will be done forward biased in the negative half cycle. And the process will repeat for another cycle for the AC wave. So the key point that we need to remember is each thyristor will conduct for pi minus alpha duration per cycle. So here we have the voltage and current waveform for the single phase half control bridge rectifier when the load that we are taking is basically the resistive load. So current and voltage will be in phase with each other. So here we can see the input voltage is sinusoidal and we are applying the pulse at a duration alpha, and then the output voltage V0 and I0, which are in phase with each other, we can see it will be conducting from alpha to pi and another alpha plus pi to 2 pi. So conduction will be in the cycle which is half wave. So during the half wave only the conduction process takes place. So this is the full wave, but when the conduction is taking place only for the half control bridge rectifier, because only we have the two diodes which is in place of two thyristors, and these are the voltage of the two thyristors T1 and T2. Let us see the waveform. The output voltage waveform consists of positive half cycle of the input voltage, which is the supply voltage Vs, and the load current waveform will follow the voltage waveform because it is a resistive load. So the conduction period for thyristor T1 will be from alpha to pi in the positive half cycle, and from alpha plus pi to 2 pi. In the negative half cycle, the thyristor T3 is in conduction. The performance parameters for the average output voltage V0, which is the DC voltage, is given by Vm by pi 1 plus cos alpha. So this Vm, which is the maximum value, can be written as root 2 times the RMS voltage. And the RMS output voltage we can get VRMS, which is in this formula. And the average load current, which is the DC current, is again the voltage divided by the resistance. So here whatever the voltage we have got it, we can substitute in this expression to get the average load current. RMS current again we can get from the RMS voltage divided by the resistance. Two important quality factors, which is the form factor and the ripple factor. So the form factor is the ratio of the RMS voltage by DC voltage, and the ripple factor is under root of form factor square minus 1. So we have already calculated this RMS voltage and DC voltage that we can put and get this expression of form factor. Ripple factor again we can get it from the form factor, which is calculated here, square minus 1. So what is the note that we have is that the form factor increases when the firing angle increases. So increase in the firing angle will increase the form factor. And if you have higher ripple factor, it will be indicating more AC content in the output. So higher ripple factor is required if you require more AC content in the output. But since it is a rectifier, we need only the DC supply at the output. So ripple is not necessary at the output. Circuit configuration, if you talk about, similar to our load case, you can have common cathode, common anode and asymmetrical mode. So there is an impact of inductance. The load current will continue to flow at the end of each half cycle. So when it is a resistive load, the current will die out, or the load current will die out as soon as the voltage is turned off. But here, due to the presence of the inductance, the current will continue to flow. So there is a freewheeling action occur through the diodes, and the current cannot change instantly due to the action of LdI by dt constraint. So whenever you have a load which is comprising of the inductance, the current will keep on flowing even the supply voltage is cut off. So here we will be taking again in the 3 configuration the load which is comprising of the resistance and the inductance. So that is the RL load configuration in the common cathode, common anode and the asymmetrical mode of controlled rectifier. So what happened in this positive half cycle, which is the conduction from omega t, which is alpha to pi, the thyristor T1 and the diode D2 will conduct. So supply voltage will directly connect across the load and the current will build up according to the RL circuit dynamics. Now, if you have the freewheeling period, which is the omega t between pi to pi plus alpha, here the input voltage will become negative. But there will be current which cannot reverse instantly. So the diode D1 comes into conduction due to the freewheeling action, and load current will flow from thyristor T1 to diode D1. The current now decay exponentially with time constant given by L by R, because it is a RL network, so time constant is L by R. In the negative half cycle, which is omega t from pi plus alpha to 2 pi, the thyristor T3 and diode D4 will conduct. The process will repeat for the negative half cycle and will complete one full cycle. There are 2 important modes. One is the continuous mode of operation, another is the discontinuous mode when there is a RL load connected. So let us see what is the continuous mode. So load current never reaches 0 in this case, but if the load current reaches 0 during each half cycle, then that is a discontinuous mode of operation. Second, it will give rectangular input current waveform in the continuous mode, and the magnitude will be equal to the load current during the conduction period. In the discontinuous mode, when the load current is reaching 0, the output voltage equals 0 when the current is 0. So both voltage and current becomes 0 together, and the conduction period depends upon the time constant, which is equal to L by R. So whenever you have a load combination RL, then you can have continuous as well as discontinuous mode depending upon the value of the parameters. So if you see the performance parameters for the RL load, the average output voltage, which is the DC voltage, is given by Vm by pi 1 plus cos alpha. Again, this expression can be written as the maximum value is equal to root 2 times the RMS voltage. So RMS output voltage is given by this expression, and for continuous conduction mode, the voltage expression remain the same as what we have for the resistive load case, but current analysis become more complex due to the inductive effect. So this expression do not change whether you are dealing with the resistive load or whether you are dealing with the RL load combination. What happen is there is a change in the current, which is due to the inductive effect that we have. The current becomes more complex. Now the other load combination that we have is the RLA load combination. So here we, along with the resistance and the inductance, we will be having the back EMFs similar to the DC motor battery. So this is the single phase half control bridge rectifier with the load which is RLA load. Operating principle, if you see, the load current flows through either the T1 or the T3 and one diode. Positive half cycle will have D1 and D2 conduction when omega t is equal to alpha to pi, and the negative half cycle you will have T3 and D4 conduction. So omega t will be pi plus alpha to 2 pi. Now in the freewheeling through T1 and D1 or T3 and D3 in the negative half cycle, the current will not flow through the load, but it will freewheel through the freewheeling diode. So that will increase the efficiency. So let us do the continuous load current mode. The operating condition is load current is always greater than 0. So in the continuous mode, you cannot have the load current which is 0. It will be always greater than 0. And the voltage equation during the conduction process, you can write as root 2 V sin omega t. This is the input voltage. And the KVL equation will give you the voltage across the inductor, which is L di by dt, the voltage across the resistor, which is R into I naught, and the battery voltage E for omega t alpha to pi. Current expression, which is the transient expression, having the steady state as well as transient, will depend upon the load impedance. It will depend upon the load power factor angle, that is tan phi, which we can compute, and the sin theta also, which is computed by E by root 2 V. So these all things we have discussed in the previous lectures in detail, and the time constant is again L by R. So this is the current expression that we have in the RL load combination. Some of the key characteristics that we have in the continuous mode is that the load current is continuous and always positive. Output voltage will flow input voltage through during the thyristor conduction. Output voltage is 0 during the freewheeling period. T1 conducts from alpha until T3 is fired at pi plus alpha. So here your current will not be negative, it will always be positive. That is the most important point to be remembered in the continuous mode of operation. In the discontinuous mode, what is the difference is that the load current will now become 0 for certain time period. So that is what we call discontinuous. So operation sequence, if we talk about, then when thyristor T1 is triggered at omega t equal to alpha, and if you have the output voltage which is greater than the battery voltage, then the current will start from 0 and increase. The current will increase until omega t equal to pi minus theta, where output voltage now is equal to the battery voltage. Omega t pi minus theta, output voltage will be less than the battery voltage and the current will decrease. At omega t equal to beta, the current becomes 0 before the T3 is triggered. So beta is known as the extinction angle. So during the phase of omega t from beta to pi plus alpha, no device will conduct and the output voltage will be equal to the battery EMF E. So this is the entire operation sequence for the discontinuous current mode. What are the important observation? That load current will start and ends at 0 during each half cycle. So here the load current is becoming 0 and the output voltage will equal to the battery EMF when no device is conducting. Conduction angle gamma, which is equal to beta minus alpha, and it will depend upon three important parameters, which is the firing angle alpha, what are the parameters of the circuit, resistance, inductance, and the battery voltage, and the input voltage magnitude. So that will decide the conduction angle. If you have the high inductance in the circuit, so the assumption is the inductance is very, very high, then in that case the load current is continuous and you will have negligible ripple. So the input expression of the supply voltage and the output voltage for different conduction period from omega t alpha to pi, you will be getting the output voltage I naught, and omega t from pi plus alpha to 2 pi you will have minus I naught, otherwise it will be 0. So inductance, if it is high, then the load current is continuous. This is the main point to be remembered, and you will not have any ripple in that. Fourier series representation we can do it, what we have for different harmonics component, which is 1, 3 and 5, you can have the current Is or T, which is given by this expression. And the fundamental component what you have here, the first component is basically given by 2 root 2 I naught by pi cos of alpha by 2. So that is the fundamental component of the current. There are certain parameters which estimate the power quality, that's such as the displacement factor, which is cos of the phi 1 fundamental component given by cos alpha by 2. The distortion factor, which is the ratio of the fundamental component by the current, is given by 2 root 2 by pi cos alpha 2. Power factor is the product of the distortion factor as well as the current displacement factor. Harmonic factor is again estimated as a square root of current distortion factor square minus 1. So these are certain power quality parameters. When we do the power analysis, the active input power, which is the product of voltage, current and cos of alpha by 2. So here we are taking the fundamental component. So that is given by this expression. In the reactive power, instead of cosine expression, we will use the sine expression. So we have voltage multiplied with current multiplied with the sine of alpha by 2. So this is what we have, the reactive power input. What is the power factor implications? That power factor will decrease as firing angle alpha increases. And the extremities, if you check at alpha 0 and alpha 90, what happen? Alpha 0 maximum power factor you will get close to 1 and alpha 90 power factor will be close to 0.45. Now we will see what is the effect of transformer leakage inductance. So here we have a circuit which is a single phase full wave control rectifier. Now you are having center tap transformer with RL load and leakage inductance. So here you have the transformer and this is the input voltage which is AC. If you see at the output, there is RL load combination what you have and there is inductor connected with the thyristor. So this inductor is known as the leakage inductance. Now what is the importance of this leakage inductance? We will see. So the circuit component now having center tap transformer with the leakage inductance LC and two thyristors with a RL load combination. So here the output of the secondary is center tapped, which is connected to the load. If we talk about the commutation process, then the current cannot transfer instantly between the two thyristors and hence the finite commutation time is required. The commutation overlap interval U occurs and during the overlap both thyristor conduct simultaneously. So what is the meaning that thyristor T1 and T2, there are two thyristors. If thyristor T1 is off, then thyristor T2 should start conduction. But a time occurs when both the thyristor is conducting and none of the thyristor is off. So there is a overlap in that. So that interval is given by U. So the physical interpretation is that the leakage inductance, which is connected LC, it will oppose the sudden current which is changing and it will cause gradual transfer of current from outgoing to incoming thyristor. So suppose T1 is turned off and T2 is turned on, then the leakage inductance LC will play here important role. It will oppose whatever the sudden change is there in the current when one thyristor is turned off and another thyristor is turned on. So if you do the commutation analysis process, so initially what happened, one thyristor was conducting the full load current and at omega t equal to alpha, the second thyristor is triggered. So during the overlapping period, which is alpha to alpha plus U, both the thyristor is conducting now. So current is transferring gradually from first to second thyristor. Now there is a short circuit which is occurred in the transformer secondary. So omega t equal to alpha plus mu, this is the commutation complete time period. So this overlap angle can be estimated using this expression where cos of alpha plus U is equal to cos alpha minus one expression which is 2 omega LC into IA divided by root 2 V, where omega is the frequency and LC is the leakage inductance, IA is the current. So voltage reduction is there during the commutation. So there is a voltage drop which will take place during the commutation process. So what is the average voltage drop that you have can be estimated from this expression, which is again given by this expression, which is 2 omega LC IA by pi. Actual average output voltage that you get, VDC, which will be little bit less because we have to subtract this drop whatever we have from the actual DC expression. So the key insight that you have is that average output voltage will be reduced by the commutation reactance, and voltage drop is proportional to the load current. So if you see the voltage drop, it is proportional to the current what you have. Higher leakage inductance will cause greater voltage drop. So if you have more leakage inductance connected with the thyristor, then you will have greater voltage and drop. Now we will have the full wave control bridge with source inductance. So here we have, you can see the inductor is connected with the source. So it is a source inductance, and rest part of the circuit, here you have the full wave rectifier with the RL load combination. So there are 4 thyristors what you have in the bridge configuration, because it is a full wave controlled bridge rectifier, and there is a source inductance which is LC connected, and what you have is the assumption is that continuous conduction will take place and ripple free load current you will be getting. So at the load, which is a combination of resistance and inductance, since there is a inductor, you may have got the ripple, but when you have the source inductance, you will be getting ripple free load current, and the conduction process will be continuous. What is the effect of the source inductance? Output voltage not constant during the conduction period. So input current waveform will change significantly, and the commutation overlap will occur between the thyristor pairs. So these effects that we have seen for the source inductance, you will have the commutation overlap generally take place between when the thyristors are conducting. So if you see the commutation process in the bridge rectifier, what is the sequence? So initially the thyristor T3 and T4 was conducting, and at omega T alpha, thyristor T1 and T2 are triggered. So overlapping period when alpha 2 alpha plus U, all 4 thyristor will conduct. So load current will free will through all the devices, and the output voltage will become 0. Input current will change when the polarity with the change gradually. So omega T alpha plus U, the thyristor T3 and T4 will be turned off. This is the mathematical analysis of the commutation. If we talk about the voltage equation during the overlapping period, the voltage is LdI by dt during the omega T from alpha to alpha plus U, and this Vs is given by root 2V sin omega T. So what is the current during the overlapping period, which is given by this expression, which is depending upon both the alpha, which is the firing angle, as well as the frequency omega T also. Overlap angle can be estimated by this expression, which is cos alpha minus the drop. If you remember, this is the drop that we have in the voltage, and the corrected average output voltage that we get is basically the actual voltage minus the drop that you have, 2 omega LSIA by pi. Equivalent circuit model with commutation resistance. So this is a simplified model where you have the DC voltage source, which is 2 root 2V by pi cos alpha, and the commutation resistance is connected RC, which is 2 omega LS by pi. So this is the simplified model of the circuit. Series combination will represent the rectifier behavior. What is the physical meaning? The commutation resistance will represent the voltage drop across the source inductance, and there is a power loss during the commutation period. So during the commutation period, there will be some power loss in the circuit. This is the voltage and current waveform during the commutation overlap effects. So input voltage we have sinusoidal in nature, which is the AC supply. Output voltage will be reduced during the commutation overlap. Load current will be continuous and smooth, and the thyristor current will show overlap period. Input current will be trapezoidal shape due to the commutation. So here you can see the input current, which is in the form of trapezoidal. So that is what you have. And if you see the thyristor current, it is showing the overlapping period. So there is a period for which both the thyristors are in conduction. So if it is a full wave, all the 4 thyristors will be in conduction, and there will be overlapping. Fundamental performance parametrics like the rectification efficiency, which is the power output, that is a DC, by power input, which is AC, can be calculated as the product of the corresponding voltage and current, and efficiency we can compute from power output by power input expression. Form factor is the ratio of RMS voltage by DC voltage, and ripple factor is again square root of form factor square minus 1. So these performance matrices are used. Some of the quality indicators are: lower ripple factor will indicate better DC quality. it is well known that ripple factor has to be less. Higher efficiency if you have, then it is indicating that better power conversion is there. And for ripple free load current, your ripple factors, the ratio has to be equal to 0. Current ripple factors should be 0. Now this is my fundamental current, but you have in the RMS, which is given by 2 root 2 IA by pi under root of 1 plus cos alpha. We have not shown the derivation here, just the final expression. The displacement factor is given by cos of phi 1, which is equal to cos of alpha t. Current distortion factor, which is 2 root 2 by pi 1 under root of 1 plus cos alpha. The overall power factor is the product of current distribution displacement factor into the distortion factor. And the power component that you have, the active power and the reactive power, can be calculated from Vi cos phi and Vi sin phi expression. Now, if you do the performance comparison for the different loads, that is the resistive load, RL load and RLE load, the average voltage, if you see for the RL load and RLE load are same, and for R load, you can compute by this expression, which is same for the resistive load. Current mode, which is discontinuous in resistive, but in RL load, you can have continuous or discontinuous, similar for the RLE load. Freewheeling action in resistance, not required, but both you have yes. Back EMF, there is no back EMF in R load. Even in RL load, you do not have, but here RLE load, you have back effect, EMF effect. Control range, if you see alpha from 0 to 180 degree for R load, here also 180 degree up to conduction, and it is limited by the value of the back EMF which is connected. So some of the key difference, if you see, R load is the simplest in analysis. Current will follow the voltage. In the RL load, freewheeling will improve the current continuity, and when you have the RLE load, back EMF will limit the control range and affect the mode of operation. So design consideration, if you talk about, then the advantage is that it has the reduced cost when you have the fewer thyristors. So 2 thyristors are already replaced. So control circuitry is also simple, and there is a natural freewheeling through the diode and good performance for many applications. What you have disadvantage, the power factor is lower as compared to full controlled rectifiers. You have higher harmonic content, and there is a limited control range with back EMF loads. Voltage drop is there due to commutation inductance. Some of the applications what you have is the DC motor drive with moderate performance requirement, battery charging systems, and DC power supplies with cost constraint. So there we are using basically the controlled rectifiers with half controlled. So let us discuss the conclusion that we have done for this. Circuit configuration of half controlled bridge rectifier use 2 thyristors plus 2 diode. Common cathode configuration are the most widely used, and different load types require different analytical approaches. Operating characteristic, if you talk about, then there are 3 important loads: R load, RL load and RLE load. R load current will be discontinuous and it will follow the voltage waveform. In the RL load, freewheeling action will be there and the current can be continuous or discontinuous depending upon whether you have high inductance or low inductance. RLE load, you have back EMF which is affecting the conduction process, and the mode depend upon the load parameters. Practical consideration, leakage or source inductance cause commutation overlap. So whenever you have leakage inductance or the source inductance, it will cause the commutation overlap. There will be reduction in the voltage and the current waveform will also be altered. So it can be modeled using the equivalent circuit using the commutation process where you have a source and the resistance in series. Performance parameters, if you do it, so average output voltage is given by root 2 V by 1 plus cos alpha. Power factor decreases with increasing the fire angle. Harmonic distortion will be significant due to non-sinusoidal nature of the input current. Commutation effect will reduce the output voltage by a factor 2 omega L into IA by pi. Design guidelines, choose the firing angle based on the voltage regulation requirement. Consider the power factor implications for AC supply. Account for commutation effect in the practical design and use appropriate filtering method for output ripple reduction. This completes our discussion on half controlled. In the next lecture, we will see about the full control, and then we'll complete our discussion on the converter. So dual converter is also remaining, so that we will complete with the control rectifier. Thank you for now.